Free energy. Nikola Tesla secrets for everybody. First secret. All of Tesla's secrets are based on electromagnetic feedback. Explanation: an ordinary energy system comprises a generator and motor, common view, and can be completed with an electric current feedback as shown here in electrical circuit. A. Electrical feedback, electromagnetic field feedback. In case A, the system once started, will slow down and stop because of friction, resistance and so on. Nikola Tesla arranged a feedback loop for the electromagnetic field, case B, and he said, electromagnetic field feedback destroys the interaction symmetry. This means that an action no longer has an equal and opposite reaction. In case B, once started, the system will accelerate in spite of friction, resistance and so on, provided that the phase of the electromagnetic feedback is positive and is sufficiently large. In order for an electromagnetic field to exist in a motor, there must be some energy input, and Tesla said, energy generation by its own application. Question: how can you produce positive electromagnetic field feedback? An answer: the simplest and well-known example is Michael Faraday's unipolar motor, as modified by Nikola Tesla. An ordinary unipolar motor consists of a magnetic disk, and a voltage applied between the axis and a point on the circumference of the disk as shown in A, above. But an ordinary unipolar motor can also consist of an external magnet and a metal disk with a voltage applied between the axis and a peripheral point on the disk as in B, above. Tesla decided to modify this version of the unipolar motor. He cut the metal disk into helical sections, as shown here. In this case, the consumption of current produces an additional magnetic field along the axis of the disk. When the current-carrying wires are tilted in one direction, their magnetic field augments the main external magnetic field. When the wires are tilted in the other direction, their magnetic field reduces the main external magnetic field. So, the current flow can increase or reduce the external magnetic field of the unipolar motor. Amplification is not possible without applying power. If it is possible to arrange a magnetic field feedback loop for mechanical devices, then it is probably possible to arrange it for solid-state devices like coils and capacitors. The other parts of this article are devoted to devices which use coils and capacitors. All of the examples in this article are only intended to help your understanding of the principles involved. Understanding would be made easier if we pay attention to the ferromagnetic shielding of the second coil in the transformer invented by Nikola Tesla. In this case, the ferromagnetic shield separates the first and second coils in the transformer from each other, and that shield can be used as magnetic field feedback loop. This fact will be useful for understanding the final part of this article. It is also helpful to consider the properties of the electrostatic field. Electrostatics. Scalar field and the longitudinal electromagnetic waves. Comment: Mr. Tesla said, there is radiant energy, perpendicular to the surface of any charged conductor, produced by a scalar electromagnetic field, thus giving rise to longitudinal electromagnetic waves. At first glance, this contradicts the age-old experience in studying the electromagnetic field. According to modern concepts, any electromagnetic field has components which are perpendicular to the direction of the propagated electromagnetic wave. Also, Maxwell's equations describe an electromagnetic field as a vector. However, the first impression is erroneous, and no contradiction exists. Definitions of physics: any conductor has both inductance and capacitance, that is, the ability to accumulate charge on its surface. A charge on the surface of a conductor creates an electric field, electrostatic field. The potential, voltage, at any point of the electric field is a scalar quantity. That is, it is a scalar electric field. If the electric charge of the conductor varies with time, then the electrostatic field will also vary with time, resulting in the appearance of the magnetic field component. Thus, the electromagnetic wave is formed, with the longitudinal component of E. Remark: in order to understand how a longitudinal wave interacts with conductive bodies, one needs to read the section of electrostatics entitled Electrification by Influence. Particularly interesting are Maxwell's equations, where they mention the displacement current. Now we come to the first secret. Secret 1. The power source in Nikola Tesla's free energy device, the amplifying transformer, is a self-powered LC circuit. Explanations. An example of unlimited voltage rise. Based on batteries and a switch. Explanation: batteries 1 and 2 are connected to the capacitor C alternately, through the inductances L. Voltage on capacitor C and the voltage from the batteries are increasing. As a result, there can be unlimited voltage rise. When the voltage on the capacitor reaches the desired level, it is connected to the load. Comment: 2 diodes were used to avoid synchronization requirements. Manual or relay switching can be used. One implementation used a spark gap to connect the output load, but a switch is an alternative method. Timeline for the process. The schematics can be simplified, and only one battery used, load is connected in the same way. Comment: maybe Alfred Hubbard used an idea shown as option B, in some versions of his transformer. Comment: if you want to get a self-powered circuit, you have to arrange some kind of energy feedback to the batteries. But, is this an actual free energy technology? I am not sure. Comment: is this the only possible way? No, of course not, there are different ways of doing it. For example, you can use fields inside and outside of some LC circuits. How can we do that? For more secrets, read the following parts. How do we get this result? An answer. You need to charge the capacitor using the electric component of the electromagnetic field of the inductor, using the displacement current of Maxwell's equations. Explanation. When the electric field in capacitor C is decaying, due to feeding electrical current into an inductor, not shown, the external electric field generated by the inductor tries to charge this capacitor with the inductor's displacement current. As a result, the capacitor draws energy in from the surrounding electromagnetic field, and the capacitor's voltage rises cycle by cycle. Implementation A: a central capacitor is used. Implementation B: no capacitors are used. In this case, instead of using a capacitor, the capacitance between the two sections of inductor L provides the necessary capacitance. How do we start the process? In implementation A, you must charge the capacitor and connect it to the inductor to start the process. In implementation B, you must use an additional pulsing or kicking coil, which starts the process by providing a pulse in either the electrical field or the magnetic field, shown later on. How do we stop the process? The process of pumping energy can continue uninterrupted for an unlimited length of time, and so the question arises, how do you stop the device if you should want to? This can be done by connecting a spark gap across the coil L, and the resulting sparking will be sufficient to stop the process. The kicking process using an electric field. Use an additional special kicking coil, which can generate short powerful magnetic pulses, and install an amplifying Tesla coil along the electrical vector of the electromagnetic field of this coil. The electrical field of the driving pulse or kicking coil will charge the spread capacitors of the inductor, and the process will be started. Use pulses as short as possible in kicking coil, because the displacement current depends on the speed of the changes in the magnetic field. The kicking process with a magnetic field. It is not possible to kick the process by displacement of the amplifying Tesla coil in the uniform changing magnetic field of the kicking coil, because the output voltage on the ends of the Tesla amplifying coil will be equal to 0 in this case. So, you must use a non-uniform magnetic field. For that you must install a kicking coil, not in the center of the amplifying Tesla coil, but positioned away from the center. Is that all true, and the best technique to use? No, it is not. Nikola Tesla found more subtle and more powerful method: his bifilar pancake coil. Bifilar pancake coil may be the best method. The voltage between adjacent turns in an ordinary coil is very low, and so their ability to generate additional energy is not good. Consequently, you need to raise the voltage between adjacent turns in an inductor. Method: divide the inductor into separate parts, and position the turns of the first part in between the turns of the second part, and then connect end of the first coil to the beginning of the second coil. When you do that, the voltage between adjacent turns will be the same as the voltage between the ends of the whole coil. Next step: rearrange the position of the magnetic and electric fields in the way needed for applying amplifying energy, as described above. The method for doing this is the flat pancake coil, where the magnetic and electric fields are arranged in exactly the way needed for amplifying energy. Now, it is clear why Tesla always said that his bifilar pancake coil was an energy amplifying coil. Remark: for the best charging of the natural self-capacitance of the coil, you have to use electric pulses which are as short as possible, because the displacement current, as shown in Maxwell's equation, depends to a major degree on the speed of the change in the magnetic field. The dual-layer cylindrical bifilar coil. Instead of the standard side-by-side cylindrical bifilar coil, the coil winding may also be arranged in two separate layers, one on top of the other. The electro-radiant effect. Inductance in an electrostatic field. Explanation: the primary coil in Tesla's transformer is the first plate of the capacitor. The secondary coil is the second plate of the capacitor. When you charge a capacitor C from your source of energy, you charge a wire of the primary coil. Also, as a result, a wire of the secondary coil is charging also, as a return from ambient space. In order to start the process, you have to remove charge from the primary coil, by arranging a jump in potential in ambient space. When this is done, a huge displacement current occurs as a result of that potential jump. Inductance catches this magnetic flux, and you have energy amplification. If this process is operating, then you generate a magnetic field in ambient space. Comment: the capacitance of the wire of the primary coil is very low, and so it takes very little energy to charge it, and a very short spark to discharge it, without removing charge from the capacitor C. Comment: notice that the spark gap must be connected to the ground, as, in my opinion, this is a very important feature of this process, but Mr. Tesla did not show grounding. Perhaps this needs to be a separate grounding point. Remark: in my opinion, this technology was also used in Gray's device and in Smith's devices, and in both cases the spark gap was connected to the ground. Also, pay attention to the words used in Gray's patent for inductive load. And, pay attention to Smith's words: I can see this magnetic field, if I use a magnetometer. Modern implementations in self-powered LC circuits. Example 1. Using a bifilar coil as the primary coil in a resonant Tesla transformer. By Don Smith. Explanation: the bifilar primary coil is used as primary for energy amplification, and is pulsed through the spark gap. Example 2. By Mislavskij. Is comprised of two capacitor plates sandwiching a ferrite ring core with a coil wound on it. Explanation: when a capacitor is charging, or discharging, this displacement current flow generates a magnetic field in the vacuum in a circular form, Maxwell's equations. If a coil is wound on a ferrite toroid placed between the plates of the capacitor, then a voltage is generated in the turns of that coil. Also, if an alternating current is applied to the coil wound on the ferrite toroid, then voltage is generated on the capacitor plates. If an inductor and a capacitor are combined in an LC circuit, then there are two cases inside such an LC circuit: A. Energy amplification, and B. Energy destruction. The situation depends on how the coils and capacitor are connected together. Energy generation. Energy destruction. Comment: if the direction of the turns in the coil wound on the ferrite core is reversed, then the wires connecting the coil to the capacitor plates need to be swapped over as well. The first experiments with a ferrite core inside a capacitor were made in 1992 by Mislavskij, a seventh-year pupil of the Moscow school, and so it is known as Mislavskij's transformer. Prototype transformer. The same approach. By Don Smith. In this arrangement, the capacitor is charged by sparks and powerful displacement current is produced. The transformer with the ferromagnetic core is collecting this current. This schematic diagram is very rough, and lacking in details. It will not perform correctly without back electromagnetic force suppression of some kind, see below. Secret 1.1. Back EMF suppression in a resonating Tesla coil. Version 1. The primary and secondary coils, and the ground connection in this Tesla coil are arranged in special manner. Explanation: the exciting, driving, current and the load current in an electromagnetic field, are perpendicular to each other as shown here. In order to get an energy gain, the frequency of excitation of the primary coil must be the resonant frequency of the secondary coil. Excitation with just a single spark is possible. In Mr. Tesla's terminology, this is pumping charges or charge funneling. The charge is coming from the ground, which is a source of energy. Potential, voltage, distribution on the coil. Explanation: the task of the oscillating circuit is to create a local electromagnetic field with a large electrical component. In theory, it would only be necessary to charge up the high voltage capacitor just once, and then a lossless circuit would maintain the oscillations indefinitely without needing any further power input. In reality, there are some losses, and so some additional power input is needed. These oscillations act as a bait, attracting charge inflow from the local environment. Almost no energy is needed in order to create and maintain such a bait. The next step is to move to this bait to one side of the circuit, close to the source of the charges, which is the ground. At this small separation, breakdown occurs and the inherent parasitic capacitance of the circuit will be instantly recharged with energy flowing into the circuit from outside. At the ends of the circuit there will be a voltage difference, and so there will be spurious oscillations. The direction of this electromagnetic field is perpendicular to the original field of the bait, and so it does not destroy it. This effect is due to the fact that the coil consists of two opposing halves. The parasitic oscillations gradually die out, and they do not destroy the bait field. The process is repeated spark by spark for every spark which occurs. Consequently, the more often sparks occur, the greater the efficiency of the process will be. The energy in the bait experiences almost no dissipation, providing a much greater power output than the power needed to keep the device operating. Tesla schematics. Don Smith named this technology bird on the wire. The bird is safe on the wire until a spark occurs. Mr. Tesla named this technology a charge funnel or charge pump. The principle of the technology. 1. This free energy device generates an AC electrical potential in ambient space, bait for electrons. 2. Electrons flowing through the load, flow in from the environment, attracted by this bait, pumped in. Not a single electron used for exciting ambient space needs to flow through the load. Possible design for the charge pump or charge funnel. By Edwin Gray. Probable schematic for Edwin Gray's cold electricity circuit. This schematic is a simplification of Gray's patent, produced by Dr. Peter Lindemann for greater clarification in his book. Possible design for the charge pump or charge funnel. The charging system is unable to see the field inside a charging capacitor. Common view of resonance: resonance is not destroyed if you short circuit or open a pumping capacitor. You can add an ordinary, very large capacitor in parallel with the pumping capacitor for more impressive results. Don Smith illustration. You have to use an alternating E field, in order to charge the capacitor. But, Smith marked the north and south poles in his drawing. I think that this is true for only one instant. Diodes are not shown in his drawings, which indicates that his device as shown, is to my mind not complete. The external appearance of Ed Gray's tube. Gray's tube with its two internal grids is seen in the middle. Two diodes are underneath the acrylic sheet. A Leyden jar is located on the left. The HFHV coil is behind Gray's tube. A possible design for the charge pump or charge funnel. The TESTATIKA by Paul Baumann. The central electrode in the jars, capacitors, is for the excitation of ambient space. The two external cylinders are the plates of the charging capacitors. The charging mechanism is unable to see the field inside the charging capacitors. For more details, read the section on asymmetrical capacitors. A possible design for the charge pump or charge funnel. This is based on Tesla's schematics. Comment: first, you need to arrange a voltage killer barrier on one side of the Tesla coil. This is to create a blind charging system which can't see the charge on the capacitor. See below for more detail on blindness. Comments: huge capacitor means as much ordinary capacitance as possible. Effectiveness depends on voltage and coil frequency, and current in the node. Effectiveness depends also on the frequency at which the excitation spark occurs. It is very similar to Don Smith's devices. For more details, read part devoted to Avramenko's plug. Possible design for the charge pump or charge funnel. The charging system is unable to see the field inside the charging capacitor. For more details, read the part which is devoted to Avramenko's plug. An ordinary piece of wire can be used in some versions of this gadget, see below. Energy regeneration by L/4 coil. This system is based on wireless energy transmission through the ground. Energy radiated to ambient space lowers the efficiency of this process. The receiver and transmitter coils must have the same resonant frequency. Possible alternative arrangement. A metal sheet can be used instead of a long wire. The cold and hot ends of a Tesla coil. By Donald Smith. Comment: if the excitation coil L1 is positioned in the center of coil L2, then the Tesla coil will have a cold end and a hot end. A spark gap can only be connected to the hot end. You cannot get a good spark if the spark gap is connected to the cold end. Volts represents the more negative and amperes the less negative. Therefore the electrical charge of more negative must seek the less negative to regain ambient. Potential power is present in a bar magnet as shown. The source of these electrons, being from the solar plasma, are non-ionic and occupy all free space. They are commonly obtained from air and earth groundings. They exist in doublet pairs, one being more negative than the other. The more negative one has left-hand spin. The less negative one has right-hand spin. Resonate electrical coil systems are analogous to the system observed in the bar magnet above. The block wall area is located at the base of L2 coil. The left spin portion, voltage only, part of the coil predominates the right-hand spin portion. Magnetic amperage portion is mostly absent. It is easy to understand the hot and cold ends, if one end of the Tesla coil is grounded. The grounded Tesla coil a hidden form of energy. Explanation: we can look at the Tesla coil as a piece of metal. Every piece of metal can be charged. If Tesla coil is grounded, it has an extra charge delivered from the ground, and has an extra energy also. But it can be found out only in electrostatics interactions, not in electromagnetic one. This diagram shows only one instant. After half a cycle, the polarities will be swapped over. Question: how can we use this fact? Answer: we have to arrange an electrostatic interaction. Extra capacitors can be used for charging them. This looks like Smith's plasma globe device. Maybe he used this technology. This can be used in charge pump technology for excitation by an alternating electrical field. Read the section on the charge pump or charge funnel. The wiring can be different to that shown above. Examples of grounded bifilar, multi-strand, coils. From Tyrell Kopanads in his 100 kilowatt device. From Stephen Mark in Big Toroidal Power Unit. From Donald Smith. Possible simulation of quarter wave cold and hot ends. Modern options in back EMF suppression. Symmetrical versions. Primary coil in Smith's device plays the same role as the rod in Gray's tube. These devices use the same principle. Both of the two out-of-phase outputs were used and both connected to the step-down transformer. 1. Between sparks, there is no current in the step-down transformer and so the two ends of L2 are at the same voltage. 2. During a spark, parasitic capacitors, not shown, connected across both sections of L2 are discharged to ground, and current is produced in the step-down transformer. One end of L2 is at ground potential. But, the magnetic field of this current in L2 is perpendicular to the resonating field and so has no influence on it. As a result of this, you have power in the load, but the resonance is not destroyed. In my opinion, these schematics have errors in the excitation section. Find those errors. Excitation by a single spark is possible. In the terminology of Mr. Tesla, this is a charge pump or charge funnel. The charges are coming from the ground, which is the source of the energy. Secret 1.1. Back EMF suppression in a resonance coil. Version 2. Primary and secondary coils are placed on a rod core. All of the coils are arranged in special manner. The primary coil is placed in the middle of the core. The secondary coil is in two parts which are positioned at the ends of the rod. All of the coils are wound in the same direction. Explanation. The electromagnetic fields produced by the resonant, excitation, current and the load current are perpendicular to each other. So, although you have power in the load, resonance is not destroyed by that output power. The load must be chosen so as to get the maximum amount of power flowing into it. Very low loads and very high loads will both have close to zero energy flowing in them. The secondary coil is shunting the primary coil, and so it has a current flowing in it even if no loads are connected. The secondary coil can be adjusted for resonance too. The rod material can be air, or other materials. Secret 1.1. Back EMF suppression in a resonance coil. Version 3, long wire usage bifilar usage. It is very much like version 1, but here, the two coils are combined into a single coil. It is impossible without back EMF suppression by Don Smith. Multi-coil system for energy multiplication. Comment, you decide how you think it was made. Maybe short-circuited coils will be useful. Read the following parts to discover more secrets. Modern options. For back EMF suppression. Version 3. Bifilar usage by Tyrrell Copenhads. The first end of bifilar coil, spark gap. The second end of bifilar coil is free, not shown. Secondary bifilar coil is not grounded. Step-down transformer is grounded. Possible schematics of the device. Ordinary coil grounded. Bifilar coil not grounded. BIFILAR usage. By Timothy Trapp. Possible core configuration for back EMF suppression. Toroidal core. An ordinary excitation winding is wound all of the way around a toroidal core. A bifilar output winding is wound around the whole of a toroidal core. Remember about the hot and cold ends of a bifilar coil. Remember about the hot and cold ends of the output coil. E-type core. Output coil consists of two parts. Excitation coil. The basis of back EMF suppression, Tesla patent. Regulator for dynamo electric machines. Secret 1.2 The spark exciting generator, SEG, charge delivering to LC circuit. The frequency of spark is equal to the resonance frequency of the Tesla coil. And the moment of exciting corresponds to the maximum voltage on the Tesla coil. Line dependent on the voltage. Square dependent on the energy. The spark delivers charge to the LC circuit. The charge Q on a capacitor C with voltage U is, Q equal UXC or U equal Q/C. Where Q is a charge delivered by one spark. During the excitation of the LC circuit by the sparks, the capacitance C is constant. After n excitations, the voltage on C will be unequal nx Q/C and, energy En will be raised as N2. In other words, if the LC circuit is excited by charges, we have energy amplification. Possible modification. High voltage transformer insulated from the ground or Tesla coil. Resonant Tesla coil. Parasitic capacitance Tesla coil or capacitor bank. Ground. Output spark. You need to understand that a feedback loop in the electromagnetic field is a changing voltage level in the LC circuit capacitor. A high voltage transformer is connected to collect the excess energy. Without synchronization. The spark exciting generator from Don Smith. Maintain resonance and get free energy. It appears that we need to charge the capacitor circuit to an energy level which is greater than that of the source energy itself. At first glance, this appears to be an impossible task, but the problem is actually solved quite simply. The charging system is screened, or blinded, to use the terminology of Mr. Tesla, so that it cannot see the presence of the charge in the capacitor. To accomplish this, one end of a capacitor is connected to the ground and the other end is connected to the high-energy coil, the second end of which is free. After connecting to this higher energy level from the energizing coil, electrons from the ground can charge a capacitor to a very high level. In this case, the charging system does not see what charge is already in a capacitor. Each pulse is treated as if it were the first pulse ever generated. Thus, the capacitor can reach a higher energy level than of the source itself. After the accumulation of the energy, it is discharged to the load through the discharge spark gap. After that, the process is repeated again and again indefinitely. The frequency of the excitation sparks must match the resonant frequency of the output coil. Capacitors 2 and 14 are used to achieve this goal. This is multi-spark excitation. Charges are pumping from the ground to 11 to 15 circuit. This device extracts charge from ambient space. Because of this, it will not work properly without a ground connection. If you need mains frequency, or don't want use an output spark, then read the following parts. Asymmetrical transformers can be used. Read the following parts. Possible seg arrangement, from Russian forum. Excitation spark. Step-down transformer. The L1 Tesla coil shown above, is energized by spark F1. Resonant, step-down transformer L2 is connected to the L1 Tesla coil by output spark F2. The frequency of F1 is much higher than that of F2. Seg without synchronization from Don Smith. 3 metal sheets are used. Pay attention to this. It must be adjusted by dimensions, materials. Possible schematic. 12-volt battery. Control circuit. Ignition coil. Copper plate. Glass plate. Aluminum plate. Metalless core transformer. Load output. An ordinary capacitor is a device for separating charges on its plates. The total charge inside an ordinary capacitor is 0, read the textbooks. There is an electrical field only inside the capacitor. The electrical field outside the capacitor is 0, because the fields cancel each other. So far, connecting one plate to the ground we will get no current flowing in this circuit. A separated capacitor is a device for accumulating charges on its plates. The total charge on a separated capacitor is not 0, read the textbooks. So far, by connecting one plate of the separated capacitor to the ground we will get a current flowing in this circuit, because there is an external field. We get the same situation, if only one plate of an ordinary capacitor is charged. So far, connecting an uncharged plate of an ordinary capacitor to the ground we get a current flowing in this circuit also, because there is an external field. Alternately charging a capacitor's plates. Avramenko's plug. Is it a free energy device? The principle, each plate of a capacitor charges as a separated capacitor. Charging takes place in an alternating fashion, first one plate and then the other plate. The result, the capacitor is charged to a voltage which is greater than that which the charging system delivers. Explanation: the external field of an ordinary charged capacitor is equal to or near 0, as noted above. So, if you charge plates as a separated capacitor, upload or download charge, the charging system will not see the field which already exists inside the capacitor, and will charge the plates as if the field inside the capacitor is absent. Once a plate has been charged, begin to charge another plate. After the second plate of the capacitor has been charged, the external field becomes zero again. The charging system cannot see the field inside the capacitor once again, and the process repeats again several times, raising the voltage until the spark gap connected to the output load discharges it. You will recall that an ordinary capacitor is a device for charge separation. The charging process of a capacitor causes electrons from on one plate to be pumped to another plate. After that, there is an excess of electrons on one plate, while the other one has deficit, and that creates a potential difference between them. Read the textbooks. The total amount of charge inside the capacitor does not change. Thus the task of the charging system is to move charge temporarily from one plate to another. The simplest free energy device. The capacitance of an ordinary capacitor is much greater than the capacitance of a separated plate capacitor, provided that its plates are close to each other. Annihilation spark. Output spark. The time between S1 and S2 is very short. This is an illustration of energy dependence in a coordinated system. This is an illustration of the so-called zero-point energy. Asymmetrical capacitor, current amplification. Input spark. Output spark. The capacitance, size, of the plate on the right is much greater than that of the plate on the left. Field after switch 1. Field after switch 2. Charges from the ground will run onto the right-hand plate until the moment when the external field drops to zero caused by the second spark, S2. It takes more charges flowing from the ground to annihilate the external field at the instant of the second spark, because the capacitance of the plate on the right is far greater. More charge means more current, so you have achieved current amplification through this arrangement. The field at the terminals of the plate on the right is not zero after both sparks have occurred. This is because a field remains due to the additional charges which have flowed in, pumped, from the ground. The simplest asymmetrical capacitors. The most simple asymmetrical capacitors are the Leyden jar and the coaxial cable, also invented by Mr. Tesla. Apart from the fact that the area, capacitance, of the plates of these capacitors is different, and they therefore are asymmetrical, they have another property. The electrostatic field of the external electrode of these devices does not affect the internal electrode. Field from external electrode. Field from internal electrode. This is caused by the fact that the electrostatic field is absent inside the metal bodies, see textbooks. This is true provided that the plates are charged separately. Capacitor triode. The third electrode is an asymmetrical capacitor. Field from input electrode. Output electrode. Input electrode. Control electrode. Dr. Harold Aspdin has pointed out the possibility of energy amplification when using this device. The principle of current amplification in the capacitor triode. You have to get zero potential on the inside of a small cylinder, on the input electrode. In this case, the charge on the external cylinder will be more than on the internal cylinder. More charge means more current, and so you'll have current amplification. In detail, the potential around any cylinder with radius r is, where Q is a charge on the cylinder. Potential inside the cylinder is the same, because if you want to get zero potential inside two cylinders, on the input electrode, you have to deliver more charge of the opposite sign to the external one, proportionally to the radius of the cylinder. A larger radius means more charge. Operational sequence. 1. Charge the input electrode from your source of energy. 2. The small cylinder, control electrode, will be charged automatically, if it's connected to the ground through a diode with the properly polarity. 3. Discharge the input electrode to zero level, for example, by using a spark. As a result there will be a zero potential on it. 4. If the external cylinder is connected to the ground through a diode with the properly polarity, it will be charged automatically with the opposite sign. But the charge pumped from the ground will more than for small cylinder, proportional to the ratio of their radiuses. 5. As a result, there is current amplification. Did Edwin Gray use this principle in his device? If so, then Gray's patent is lacking some very important details. The principle of the blindness charging system in the SEG. Output voltage here. No output voltage. The short coil is not able to see the oscillations in the long coil, because the total number of magnetic lines from the long coil which are passing through the short coil is close to zero, because one half is in one direction and the other half is in the opposite direction. This a particular case of an asymmetrical transformer. For more details read the part about asymmetrical transformers. Comments about the SEG. All back EMF schematics can be used in SEG. Excitation spark. Primary coil, placed in the middle of the secondary coil. Resonance coil is secondary coil. Rod core. Secondary, resonance, bifilar or long line coil. Primary, excitation coil. No current will be produced in the load in any of these circuits, unless there is a ground connection. Is excitation possible with just a single spark? For more asymmetry in SEG? For one spark exciting in SEG? Additional capacitor. Resonance coil is secondary coil. Version 1. Prototype coil version 2. Additional capacitor. Secondary, resonance, bifilar or long line coil. Rod core. This arrangement becomes more asymmetrical after excitation. Symmetry is destroyed by a spark. If the impedances of RA and RC are the same at the frequency produced by signal generator F1, then the resulting voltage at points A and B will also be identical, which means that there will be zero output. If the circuit is excited by the very sharp, positive only, DC voltage spike produced by a spark, then the impedances of RA and RC are not the same and there is a non-zero output. Here is a possible alternative. Please note that the position of the output coil must be adjusted, its best position depending on value of resistor RC and the frequency being produced by signal generator F1. Here is another possible arrangement. Here, the position of the output coil depends on L1 and L2. Modern options in SEG. Back EMF suppression in resonance coil. Version 3. By Don Smith. Please note that a long wire is used and one spark excitation, where additional capacitors are used to create non-symmetry. Multi-coil system for energy multiplication. KAPANADZE process. The process requires only 4 steps. Step 1. An LC, coil capacitor, circuit is pulsed and its resonant frequency determined, possibly by feeding it power through a spark gap and adjusting a nearby coil for maximum power collection. The SEG process causes the energy level in the LC circuit to rise. Power is fed via a spark gap which produces a very sharp square wave signal which contains every frequency in it. The LC circuit automatically resonates at its own frequency in the same way that a bell always produces the same musical frequency when struck, no matter how it is struck. The output waveform from the LC circuit is then manipulated to provide an output which oscillates at the frequency on the local mains supply, 50 Hz or 60 Hz typically. Finally, the oscillations are smoothed by filtering to provide mains frequency output power. All of these processes are described in Copenhagen's patents and so, no state or private confidential information is shown here. Copenhagen's process is the SEG process. As I see it, the main difference between the designs of Don Smith and Tyrrell Copenhagen is the inverter or modulator in the output circuit. At mains frequency you need a huge transformer core in a powerful inverter. Modern option. Lowering the LC frequency to mains frequency, modulation. Step-down transformer current amplification. It is possible to use square waves instead of sine waves to ease the loading on the transistors. This is very similar to the output sections of Tyrrell Copenhagen's patents. This method does not require a powerful transformer with a huge core in order to provide 50 Hz or 60 Hz. Don Smith's option, guessed at by Patrick Kelly. Mains frequency oscillator. High voltage semiconductor. There is no high frequency high voltage step-down transformer, but a step-down transformer is used for mains frequency, which means that it will need a huge core. For both schematics, you must choose the load in order to get the maximum power output. Very low and very high loads will give almost no energy in the load, because the current flowing in the output circuit is restricted by the current flowing in the resonance circuit. Illustrations for frequency lowering. Energy gain. Remarks on 1.1 and 1.2 secrets. We must consider two options. 1. Back EMF suppression. 1.1. 2. Excitation by a spark. 1.2. These options are different, however, in both cases, an increase of energy occurs due to the charges being pumped in from the ground. In the terminology of Mr. Tesla, a charge funnel, or in modern terminology, a charge pump. 1. In the first case, the problem for the oscillating circuit is to create an electromagnetic field which has a high-intensity electrical component in ambient space. Ideally, it is only necessary for the high-voltage capacitor be fully charged once. After that, if the circuit is lossless, then oscillation will be maintained indefinitely without the need for any further input power. This is a bait to attract charges from the ambient space. Only a tiny amount of energy is needed to create such a bait. Next, move the bait to one side of the circuit, the side which is the source of the charges, ground. The separation between the bait and the charges is now so small that breakdown occurs. The inherent parasitic capacitance of the circuit will be instantly charged, creating a voltage difference at the opposite ends of the circuit, which in turn causes spurious oscillations. The energy contained in these oscillations is the energy gain which we want to capture and use. This energy powers the load. This very useful electromagnetic field containing our excess power oscillates in a direction which is perpendicular to the direction of oscillation of the bait field, and because of this very important difference, the output power oscillations do not destroy it. This vital factor happens because the coil is wound with two opposing halves. The parasitic oscillations gradually die out, passing all of their energy to the load. This energy gaining process is repeated, spark by spark. The more often a spark occurs, the higher the excess power output will be. That is, the higher the spark frequency, caused by a higher voltage across the spark gap, the higher the power output and the greater the efficiency of the process. Hardly any additional bait energy is ever required. 2. In the second case, we must charge the capacitor circuit to an energy level higher than that of the source energy itself. At first glance, this appears to be an impossible task, but the problem is solved quite easily. The charging system is screened, or blinded, to use the terminology of Mr. Tesla, so that it cannot see the presence of the charge in the capacitor. To accomplish this, one end of a capacitor is connected to the ground and the other end is connected to the high-energy coil, the second end of which is free. After connecting to this higher energy level from the energizing coil, electrons from the ground can charge a capacitor to a very high level. In this case, the charging system does not see what charge is already in a capacitor. Each pulse is treated as if it were the first pulse ever generated. Thus, the capacitor can reach a higher energy level than that of the source itself. After the accumulation of the energy, it is discharged to the load through the discharge spark gap. After that, the process is repeated again and again indefinitely. This process does not require the suppression of back EMF 3. It should be noted that option 1 and option 2 above could be combined. Secret 2. Switchable inductance. The inductance is comprised of two coils which are positioned close to each other. Their connections are shown in front. Construction. When constructing this arrangement, there are many different options due to the various types of core which can be used for the coils. 1. Air core. 2. A ferromagnetic bar core. 3. A ferromagnetic toroidal core. 4. A transformer-style ferromagnetic core. Properties: tested many times with a variety of cores, the value of the total inductance Ls does not change if you short one of the inductors L1 or L2. This may have been tested for the first time by Mr. Tesla back in the 19th century. Application technique: this energy generation is based on the asymmetrical process. 1. Feed the total inductance Ls with a current I2. Then short-circuit one of the inductors, say, L1, 3. Drain the energy from inductor L2 into a capacitor 4. After draining L2, then remove the short circuit from L1, short circuit L2 and then drain the energy from L1 into a capacitor. Question: is it possible, using this method, to get twice the energy amount due to the asymmetry of the process, and if not, then what is wrong? An answer: we need to start winding coils and performing tests. Examples of coils actually constructed. A coil was wound on a transformer ferromagnetic core, the size is not important, with permeability 2500, not important, which was designed as a power supply transformer. Each half coil was 200 turns, not important, of 0.33 mm diameter wire, not important. The total inductance Ls is about 2 mH, not important. A coil was wound on a toroidal ferromagnetic core with permeability 1000, not important. Each half coil was 200 turns, not important, of 0.33 mm diameter wire, not important. The total inductance Ls is about 4 mH, not important. An ordinary laminated iron core transformer intended for 50-60 Hz power supply use, size is not important, was wound with a coil placed on each of its two halves. The total inductance Ls is about 100 mH, not important. The objective of the tests: to make tests to confirm the properties of the coils, and then make measurements of the Ls inductance both with coil L2 short-circuited and coil L2 not short-circuited, and then compare the results. Comment: all of the tests can be done with just the toroidal coil, as the other coils have been shown to have the same properties. You can repeat these tests and confirm this for yourself. Option 1: these simple inductance measurements can be carried out with the help of an ordinary RLC, resistance/inductance/capacitance, meter, such as the one shown here. The measurements taken. The total coil inductance Ls was measured without short-circuited coils, the figure was recorded. The L2 coil was then short-circuited and the inductance Ls measured again and the result recorded. Then, the results of the two measurements were compared. The result: the inductance Ls was unchanged, to an accuracy of about 1%. Option 2. A special setup was used, consisting of an analog oscilloscope, a digital voltmeter and a signal generator, to measure a voltage on the inductance Ls without L2 being short-circuited and then with L2 short-circuited. After the measurements were made, all of the results were compared. Schematic of the setup. The order in which the measurements were taken. The voltage on the resistor was measured using the oscilloscope and the voltage on the inductor was measured using the voltmeter. Readings were taken before and after short-circuiting L2. The result: the voltages remained unchanged, to an accuracy of about 1%. Additional measurements before the above measurements were taken, the voltages across L1 and L2 were measured. The voltage on both halves was a half of the voltage on the total inductor Ls. The frequency of about 10 kHz was chosen because the coil did not have parasitic resonances at this frequency or at low frequencies. All measurements were repeated using a coil with a ferromagnetic E-shaped transformer core. All of the results were the same. Option 3. Capacitor recharging. The objective was to match voltages on a capacitor, both before and after it being recharged by interaction with an inductor which could be connected into the circuit via a switch. The experiment conditions. A capacitor is charged from a battery and is connected to the inductor through the first diode, included to give protection against oscillations. At the moment of feedback, half of the inductor is shunted by the second diode, due to its polarity, while the inductance must remain unchanged. If after recharging the capacitor voltage is the same, but with reversed polarity, then generation will have taken place, because a half of the energy remains in the shunted half of the inductor. In theory, it is impossible, for an ordinary inductor consisting of two coils to do this. The result confirms the prediction the remaining energy is more than the capacitor gives to the coil, with an accuracy of 20%. Test components: capacitor 47 nanofarads, inductor LS is about 2 mH, Schottky silicon diodes BAT42. Voltage used, 12 V. The result verification for option 3. For verification of these results and in order to improve the accuracy, all measurements were repeated using alternative components. Test components: capacitor, 1.5 nanofarads, total inductance, 1.6 mH, germanium diodes, Russian, D311, charging voltage, 5 V. The result, confirmation of the previous measurements, A, shown below, the recharging accuracy was improved to 10%. Also, a check measurement was made without the second diode. The result was essentially the same as the measurement which used the shunting diode. The missing 10% of the voltage can be explained as losses due to the spread capacitor's inductance and in its resistance. Continued testing. The shunting diode was reversed and the test performed again. The result, it seems that the charge is spot on. Further testing. An oscilloscope was connected to the coil instead of to the capacitor, in order to avoid influence of the first diode, so the oscillations viewed were based on the inductance of the spread capacitors. The result, the accuracy of capacitor recharging was improved to 5%, due to the removal of the influence of the first diode. After the main capacitor was switched off, by the diode, you can see oscillations caused by the spread capacitance of the inductors. Based on the frequency of the oscillations, which were 4 to 5 times higher than that of the main capacitor, one can estimate the spread capacitance as being 16 to 25 times lower than the main capacitor. Still further testing. Testing of the oscillation circuit shunting, with the two cases combined, and without the first diode. The result, a contour, oscillation circuit, is not destroyed, but it is shunted a lot. One can explain it by considering the moments when both diodes are conducting and so, shunt the circuit. As an addition, the voltage on the down diode is shown, the time scale is stretched. The negative voltage is close to maximum. Still further testing. Charging a capacitor by shunting current in oscillation mode. Conditions: the addition of a charging capacitor of 47 nanofarads. The result, a capacitor is charging without shunting the circuit. The final voltage on it is 0.8 V, and rises and falls of the voltage depend on the value of the capacitor. The overall results of the tests, options 1, 2 and 3. The symmetry of interaction in systems with electromagnetic field feedback, as with switched inductance, appears to be violated, and this implies that this arrangement could be used to generate energy. Comment: you need to choose the load in order to get the maximum power output. Very low, and very high loads, will send almost no energy to the load. Illustration for switchable inductance. Electromagnetically coupled coils wound in opposite directions. The circuit has two kinds of currents, the main current and the shunting current. The main and the shunting currents run through the same output capacitor in one direction, if the output capacitor is discharged. There is no shunting current, if the output capacitor is charged. Illustration for switchable inductance. As Don Smith said, two detector receivers were combined, and one free energy device was constructed. Don Smith produced this explanation as a PDF file, www.free.energy.info.com/smith.pdf. The resistance of the load must be chosen so as to get the maximum possible power in it. The board does not contain an output circuit, because a couple of spark gaps and one step-down transformer can be used instead of diodes and a capacitor. This was pointed out before, so read the part which describes the suppression of back EMF. Mechanical, inertial, analog of switchable inductance. From Tyrrell Copenads. Rotation direction for the first half period. Rotation direction for both half periods. Transmission to the generator. Spring helix. Rotation direction for the second half period. Electrical output generator may be conventional or Regenx generator. Pendulum 1 metallic disc. Controlling mechanism. When one pendulum is stopping, the other is accelerating. The controlling mechanism connects the pendulums to the output generator one after the other and so maintains the oscillations. Connecting extra mass to a mechanical oscillator. Mechanical energy can be stored in any spring by compressing it or stretching it. 1. It corresponds to two positions in a mechanical oscillator. 2. When only potential energy takes place in an oscillating process. If extra mass is connecting periodically to one side or the other of a mechanical oscillator, it will be shifting without any energy loss during the oscillation process. There is no need to transfer extra mass from one position to another in an actual device, because extra mass is a disk and masses in mechanical oscillators are disks also. You only have to connect them in a variety of ways. A grounded Tesla coil is an analog of a spring with one side fixed. The principle of amplification of mechanical energy. Explanation: the principle is based on an asymmetrical flywheel, 1, consisting of a small mass and a large mass. These masses are balanced across the center of rotation, that is, are located at a distance proportional to their weights, from the center of rotation. This helps to avoid vibration when they are rotating, the same principle used when balancing a car wheel. The inertial moment of such a flywheel, 1, is analogous to the inertial moments of flywheels, 2, and 3, consisting only of large or small masses. However, from the point of view of kinetic energy, all of these examples, 1, 2, and 3, are different. This is because the kinetic energy of every mass depends on the direction and speed at which it moves, if is released during rotation. The highest common kinetic energy is in the masses of flywheel, 3, as less energy is contained in flywheel, 1, and the smallest kinetic energy is in flywheel, 2. In order to get an increase in energy, one needs to achieve a setup which is based on a spring, for energy transformation from kinetic energy to potential energy and back again, and a lever of Archimedes, for changing the point where the force is applied. Comments. 1. The simplified schematic diagrams shown here are for explanation purposes only. 2. In an actual device, you can use a spring in rotation mode, as Tyrrell Copenads did. 3. You can use disks and rings as flywheel masses, as Tyrrell Copenads did. 4. Altering one mass to another is actually achieved by connecting them in various ways. Any asymmetrical mechanical oscillator behaves as indicated above, when the potential energy of a compressed spring is transformed to the kinetic energy of moving masses. The potential energy of the spring is distributed unequally between the small and large masses. A small mass acquires more energy relative to its size than a large mass does. The sum of the kinetic energies of both masses is equal to the potential energy of the spring. This is based on Tesla's asymmetrical schematic. Flywheel: a hidden form of energy. Clarifications on mechanical energy amplification. If you don't want to lose mechanical energy when doing work, then this work must be done by an imaging force. This force is absent in an inertial coordinate system, but it is present in a non-inertial coordinate system. When in a rotational coordinate system, this force is called centrifugal force. After the work is done, the centrifugal force is low, and if you want to continue producing mechanical work, you have to use the other coordinate system where centrifugal force is high again. This is possible because linear velocity does not change. You have to provide the other support point only, and a chord, in order to produce mechanical energy again. If you want to make this mechanical work continuous, then the end of the first track must also be the beginning of the second track. You have to change coordinate system periodically. In a real situation, you have to compensate for energy loss due to friction, and so a part of the excess energy must be used to maintain the process. Illustration for switchable inductance. From Alfred Hubbard. External resonance coil. Central coil. Peripheral coil series connected. The center coil and all of the peripheral coils can grasp the same flux coming from the resonance coil. All other details are the same as in Smith's version. In other words, you can use rods as the coil core, instead of a closed ferromagnetic core. But, this is not the only option in Hubbard's device. He may have had another one, based on a different principle, perhaps the principle of energy amplification in an LC circuit as described earlier, but with switchable inductance being used. Modern options. In switchable inductance. Version 1. A coil has more inductance when some of its parts are short-circuited. The central section of the coil and its two end sections are wound in opposite directions. The coil shown in the picture above has twice the inductance. When its end sections are short-circuited, measurements made with the Chinese-built RLC test meter shown here. But, this looks like resonance in an asymmetrical transformer? Switchable inductance or symmetry destroyed by spark. The basis of switchable inductances, Tesla patent. Regulator for dynamo electric machines. Secret 3. The asymmetrical transformer. With a magnetic field feedback loop, evolution of the second secret. Lenz's law is violated in an asymmetrical transformer. Therefore it is not possible to use it as an ordinary transformer. An asymmetrical transformer can have two coils, L2 and LS. Coil L2 is wound on one side of the toroidal core while LS is wound so that it encloses both the toroid and the coil L2 as shown here. Optionally, this arrangement can be implemented with a wide range of styles of transformer core. One option is to use the above, switched inductor, arrangement and add one more coil. Now that you understand the operational principles of the system, you can use any configuration which you need. For example, illustration for an asymmetrical transformer of some kind. The mechanical equivalent of an asymmetrical transformer. This example shows an ordinary transformer, wound on an E-core plus an external excitation magnet. The magnet orientation may be different. In other words, L2 is still used, but instead of LS the exciting magnet is used. The result. 1. The voltage developed across coil L2 depends on the number of turns in L2, but the short circuit current through L2 does not depend on the number of turns in coil L2. 2. You need to choose the load connected to L2 in order to get the maximum power output. Very low, and very high loads, will give almost no power output. Resonance in an asymmetrical transformer. The first coil is used as a transmitter of energy, and the second coil as a receiver of energy. It is very like radio broadcasting, where the receiver is located far away from the transmitter, and has no feedback. The first coil works in parallel resonance and the second coil in serial resonance, although the two schematic diagrams look alike. Parallel resonance for transmitter. Serial resonance for receiver. You can get much more voltage on L2 than on LS. An experiment. Conditions: the resonance frequency is about 10 kHz. The total inductance Ls is 2.2 mH, the L2 inductance, same as the L1 inductance, is 100 mH, the ratio Ls, L2 is 145 with an E-shape core, permeability is 2500. The result, at the resonance frequency, there can be a voltage which is 50 times more on any parts, L1 or L2, matched with the total coil Ls, and voltage changes on R are no more than 15%. The phase shift in voltage is about 90 degrees between Ls and L2. The amplitudes were equalized. Further, an additional step-down coil LD was wound around L2, turns ratio 50, 1, matched with L2, and the load resistor RL equal 100 ohms was connected to it. The result. Changes in current consumption, estimated by measuring the voltage across R, are no more 15%. Modern options in usage of an asymmetrical transformer. By Don Smith. Between sparks, L2 has a voltage on its ends. If RL is connected directly to L2, then there will be no output current without resonance, and there will be no output current without a spark. More accurate. L2 has no voltage on its ends, without a spark. This is ordinary back EMF suppression, invented by Nikola Tesla. L2 has no voltage on its ends, without a spark. Secret 3.1 The asymmetrical transformer based on the short-circuited coil. Introduction. Voltage distribution on the shorted coil depends on the position of the exciting coil. Description. Case 1 The excitation coil is centered. Result, we have the full period of the voltage distribution on the short-circuited coil. No orthogonality in this part. Voltage distributions are orthogonal. Case 2 The excitation coil is on one side. We have half period of voltage distribution on the short-circuited coil. Short-circuited ordinary coil. Excitation ordinary coil. Construction of the asymmetrical transformer. Based on the short-circuited coil. Case 1 The short-circuited coil is wound in one direction. Core inside is optional. The output does not influence the input in any way. The signal from the output coil generates zero voltage difference on the input coil. The position of the coils should be adjusted in order to give the best result. Case 2, the short-circuited coil is wound in opposite directions from the center outwards, and only half of the coil is short-circuited. The output has no influence on the input coil. The signal from the output coil generates zero voltage difference on the input coil. The position of the input coil needs to be adjusted to get the best result. The coil's position depends on permeability of the core. More permeability means more alike with distribution pointed at the beginning. To find the best coil position, connect the signal generator to the output, and then find the coil position which shows 0 at the input terminals. Alternatively, use an RLC meter connected to the input terminals and then find the coil position which gives no change in reading when the output terminals are short-circuited, for both case 1 and case 2. The length of the wire, the total length of the coil, and the diameter of the coil are not important. The number of turns in the input and output coils plays the same role as in an ordinary transformer, for both case 1 and case 2. Modern applications for short-circuited coils. Electrical energy generating system. Resonance input circuit. Shunting capacitor. The position of the coils must be adjusted until the output has zero influence on the input. None of the input energy used for exciting ambient space should appear in the load. The output coil can be adjusted to resonate with the input coil, but this is not important for understanding the principle. Excitation with just one spark is possible, not in resonance, but the frequency of the sparks influences the output power directly. Don Smith used the simplest doubling excitation frequency. Resonance frequency of the circuit is about 60 to 70 kHz, but dimmer is for 30 to 35 kHz. For adjusting the excitation frequency, voltage/frequency technology was used. You have to adjust two parameters, the position of the slider and the excitation frequency. Modern application for short-circuited coils. By William Barbet. U.S. Patent Application Number 2007/00078844. Self-sustaining electric power generator utilizing electrons of low inertial mass to magnify inductive energy. In order to understand this device, you have to read Barbet's patent application US 2007/00078844A1, www.freenergyinfo.com/patd25.pdf. I would like to point out that externally, it looks very much like Alfred Hubbard's device. This is Hubbard's device. Short-circuited coils inside. Exciting coils. Adjust the positions of the coils to get the best result. An example of Case 1. By Stephen Mark Toroidal Power Unit. An idea: an asymmetrical transformer based on the shorted circuited coil. positions of the coils must be properly adjusted, in order to have no transmission feedback from the output to the input. To understand this better, read the part which is devoted to switchable inductance. The first layer, shunted coil wound around the whole core. The second layer, coils for input and output. Voltage distribution. The basis of the toroidal power unit Tesla patent. Actual toroidal power unit. The position of the coils must be adjusted. The easiest way to do this is to add or remove turns at the ends of the coils. An example of case 2 by Tyrell Kopanad's mechanical device. Modern use of short-circuited coils by Cherepanov Valera, SR 193 in Russian Forum. This arrangement can be used for back EMF suppression in resonance, spark excited, mode to get a laser effect, very exciting summation effects. This was copied from this device of Tyrell Kopanad's. Mr. Tesla said, the optimum relation for the main and additional coil is 3/4 L and L/4. Is that ratio used here? If you don't understand this schematic, look at simplest version of the coil. The simplest version where the output has zero influence on the input. Position of the coil must be adjusted. This is an instance of case 1 where the output coil was removed, and some of the turns from the short-circuited coil were used instead. The asymmetrical transformer, based on a short-circuited coil, combined with a step-down transformer. The relationships of Don Smith's toroidal power unit size and position are important. Those relationships are used to produce an asymmetrical transformer. Mechanical analog of the asymmetrical transformer case 2. Any asymmetrical transformer must be adjusted. Don Smith placed magnets inside the coils, but that is not important for understanding the process as his device does not match the schematic. Some remarks on asymmetrical in-front connection. Some turns were added on one half of the coil, and some turns were removed from the other half. An additional magnetic field H3 was created, with inductance, LD. A large part of the total inductance acts as an inductor, and a small part acts as a capacitor. This is a well-known fact, read books. The total voltage on the coil is less than on its halves. Yellow the voltage on the total coil. Red the voltage on the large section of that coil. Result, the voltage on its halves is 4 times the voltage on the total coil. The measurements were made in the frequency band 10 kHz to 100 kHz. Here is the result of a capacitor discharging into this coil. Secret 4. Current amplification. If a lot of asymmetric transformers are placed with a common flux flow through them, they will have no influence on this flux flow, as any one asymmetric transformer does not have any influence on the flux flow. If the secondary L2 transformer coils are then connected in parallel, this produces current amplification. As a result, you have an asymmetric transformer arranged in a stack. For flat, uniform, field inside of LS, it can be arranged with additional turns at its ends. Examples of coils which were actually constructed. The coils are constructed from 5 sections, made from E-type ferrite core with a permeability of 2500, and wound using plastic-covered wire. The central sections L2 have 25 turns, and edge sections have 36 turns, to equalize the voltage on them. All sections are connected in parallel. The coil LS has field flattening turns at its ends, and a single layer winding LS was used, the number of turns depending on the diameter of the wire used. The current amplification for these particular coils is 4 times. Changing LS inductance is 3%, if L2 is short-circuited. Secret 5. The power source in Nikola Tesla car red arrow is ferromagnetic resonance. To understand electromagnetic feedback, you must consider the action to be like that of domains which have a group behavior, or alternatively, spin waves, like a row of standing dominoes falling over where each one is toppled by the previous one hitting it. The basis of ferromagnetic resonance. When a ferromagnetic material is placed in a magnetic field, it can absorb external electromagnetic radiation in a direction perpendicular to the direction of the magnetic field, which will cause ferromagnetic resonance at the correct frequency. Ferromagnetic rod. This is an energy amplifying transformer invented by Mr. Tesla. Question: what use is a ferromagnetic rod in free energy devices? An answer: it can change magnetization of the material along magnetic field direction without the need for a powerful external force. Question: is it true that the resonant frequencies for ferromagnetics are in the tens of gigahertz range? An answer: yes, it is true, and the frequency of ferromagnetic resonance depends on the external magnetic field. A strong magnetic field produces a high frequency. But with ferromagnetics it is possible to get resonance without applying any external magnetic field. This is the so-called natural ferromagnetic resonance. In this case, the magnetic field is defined by the local magnetization of the sample. Here, the absorption frequencies occur in a wide band, due to the large variations possible in the conditions of magnetization, and so you must use a wide band of frequencies to get ferromagnetic resonance. A possible process for acquiring free energy. 1. Subjecting a ferromagnetic to a short electromagnetic pulse even without an external magnetic field, causes the acquisition of spin precession, domains will have group behavior, and so ferromagnetics can easily be magnetized. 2. Magnetization of ferromagnetics can be by an external magnetic field. 3. Energy acquisition can be as a result of strong sample magnetization caused by an external magnetic field of lesser strength. Comment: you must use synchronization for processes of irradiation and magnetization of the sample. Useful comment: a ferromagnetic shield will not destroy the inductance of any coil placed inside it, provided that the ends of that coil are positioned on one side of the coil. Ferromagnetic shield, pipe. But, this coil can magnetize the ferromagnetic shield. Secret 5 continuation. 2 perpendicular coils on a common axis. Standing waves, spin waves, domino effect, laser effect, open resonator, etc. Explanation: standing waves can be excited not only in Tesla's horseshoe magnet, but also in Tesla's ferromagnetic transformer, excited by sparks. Excitation can be arranged in different ways, by coils connection. The frequencies of oscillations in a coil depends on the number of turns in it. A big variation is possible due to this factor. The positions of the coils on the rods depends on whatever ferromagnetic material is being used, and on its size. The optimum arrangement has to be determined through experimentation. A transformer can have 2 pairs of coils, exciting, tubes, resonance or load, inside. See Tesla's picture. Toroidal version of an asymmetric stacked transformer. An inductor L2 is placed on the central ring between the short circuits of the core, and the coil LS, not shown, is wound around all 3 rings, covering the whole of the toroid. This is an ordinary toroidal coil. The number of short circuits depends on your requirements, and influences on the current amplification. That is all. Good luck. Conclusions. 1. The energy conservation law is a result, not reason, of symmetrical interaction. 2. The simplest way to destroy symmetrical interaction is by using electromagnetic field feedback. 3. All asymmetrical systems are outside the area covered by the energy conservation law. The energy conservation law cannot be violated. The field covered by this law is only symmetrical interactions. No private or state secrets are contained in this document. There are no ready-to-use schematics in this document, as all diagrams are only provided as an aid to understanding the principles involved.